Hey guys, as promised, when we were going through our key features with graphing rational functions, we were struggling to kind of organize all of our different pieces with our graphs and our different kinds of equations. So I wanted to give you a central location and kind of a walkthrough video of how to graph rational functions given some different scenarios. So in this video, we are going to talk about how to find holes, vertical asymptotes, horizontal asymptotes, x and y intercepts, domain range, intervals of increasing and decreasing, and in behavior of our rational functions given either a graph, which is the first part of that graphing practice, the general form rational function with the h and the k kind of set up, and then our rational functions with higher polynomials. So that is what we're going to walk through when we do this. So on that practice sheet, this is going to be question 1. So this should look familiar on that sheet. Notice I've added this secondary column. You'll notice it in the other questions as well. That's not on your sheet, but this is to help you guys kind of take some notes or jot down some things so that as I work through question 1, you'll be able to be successful with all of the other graphing questions on this sheet. And also for obviously your formal and for your NCFE and EOC eventually. So holes. How can I find a hole from a graph? Well, if we notice on this graph, I visually don't see any. So how can I find these? I'm going to visually look for them. What they would look like is actual holes on your graph, just like this one. Or maybe it's over here. Or maybe there's multiple ones. Either way, you are visually looking for something that has a physical hole in it. So in this one, we have none. Vertical asymptotes. Vertical asymptotes are going to be your imaginary, it's not going to be drawn out for you like it is here, but this red line here. So x equals the vertical dotted line. Sometimes the dotted line is drawn for you, sometimes it's not. In this case, I did, just so you guys would see it. So at x equals +1, that is our vertical asymptote. Our horizontal asymptote is going to be y equals our horizontal line here that separates the two. So y equals -2. Again, these are lines that our graphs do not cross. They do need to be x equals and y equals because we are talking about a vertical and horizontal line. So those are equations for lines. Your x-intercepts. Notice this also says approximately. On graphs, we can't really exactly pinpoint where it's at because we don't have a function to evaluate in this case. So we are going to approximate. So we would put 0 in for y on the x-intercept. So anywhere on the x-axis where it crosses. So it crosses right about here at, I'm going to call it 2.5, 0. Our y-intercept is going to be about the same. So we're going to find where x is 0 on the y-axis. And that's going to be about -5. So 0, -5. So your 0 is the opposite of what you're looking for. X-intercept, y equals 0, y-intercept, x equals 0. Domain range. Domain, if we only have one vertical asymptote, and if we had multiple, we would kind of skip around with our vertical asymptotes here, like when we talked about having multiples. So we're going to go from -infinity, this direction, up until our vertical asymptote right here, which is at 1. So I'm going to come all the way -infinity up to 1, skip over 1, so I need a union. So, boop, I'm going to stop, jump over it, and then keep going. So then 1 to +infinity. So that is just the only value I don't want. Remember, we also talked about this could be all reals except one. That would also be acceptable. It just depends on the notation that they're looking for. Similarly, range, going from bottom to top, we're going to come all the way up until this horizontal asymptote here at -2. We're going to reach it, jump over it, boop, and then keep going. So at -2 is where we have that horizontal asymptote. We're going to jump over that. Increase and decrease. So this here is a positive function because I have the two pieces of my rational function mostly in what we would consider like a quadrant 1, quadrant 3 kind of happening here. It can cross over. It's just in this 4 corners. It is in your top right and your bottom left. So this would be considered positive. If it's positive, there is none. So we have no increase. It is all decrease. If it is the same as your domain because you are literally, and this is mostly just for rationals. If we're talking about polynomials and we have some hills going on and some increases, then decreases and increases again, obviously your intervals are going to change for that. But in this case with just domains, this is going to be the general format that we follow where it's typically the same as your domain. Now the end behavior is a little bit different from what we're used to. We still have the same notation here as x goes to -infinity. So as x is going to the left of my graph, where is my function going so I can follow it all the way up? And it's getting closer and closer to this horizontal asymptote. So that value at y equals -2, that is the value that it's approaching. The same as if I start and go as x goes to positive infinity and I follow it out towards positive infinity, I can imagine if I extended both of these that it would get closer and closer to the horizontal asymptote still at -2. But as we know, they approach it from different sides. So it approaches a number, your horizontal asymptote. If it's positive, it'll be from below, like we saw right here. So it approached that -2 from the bottom. And on the right side, as x goes to positive infinity, it's still your horizontal asymptote but from above. If your function is negative, you would switch the below and the above. Notice you don't need to write that in your notation, but it's just a general idea so that you kind of get the concept of what that's talking about. Higher mass, it does make a difference, but for now, it's just going to approach that horizontal asymptote. Go ahead and pause your video here. Take some notes if you need to. Ask questions if you need to. We will go ahead and move on to the next question. This is going to be question 7 from your practice problem. Notice I've already kind of set up some things here for us. So our numerator, our denominator, what we call our outside of our function, that would be our k value. And we still have our restrictions that come from our denominator. So x cannot be -4. If x is 4, then we divide by 0. And 0, there's no number that has a factor of 0, so we can't divide by 0. So this is what we call your general form. It's got your h and your k value. And so we're going to run through all these different pieces and how to find them given this specific form. So wholes, how can we find wholes given this form? Well, algebraically, we're looking for things that cancel. So if there is something in your denominator that cancels with your numerator, that would be your whole. You would take that value, plug it back in to your simplified after you canceled it out to find the associated y, because your whole would be an estimated point, and that point cannot be on the graph. So you're finding the point, but the point doesn't exist. It's kind of complicated, but it makes some sense if you kind of look at it. It's like running on a highway and you run across a pothole. Like the road should be there, but it's not there. So you have to estimate where it's at, and that's how you would do that. But in this case, we have no hole. Your vertical asymptotes still come from your denominator, and it's the factors in the denominator that didn't cancel. So we're going to have a vertical asymptote at x equals -4 because you find the root. So x equals -4. Set that equal to 0 and solve. Your horizontal asymptote is really easy in this case because it is your k value. Is your value on the outside. So y equals -3. Your x-intercepts are kind of tricky in this case. So let me just go ahead and get us ready for this. So your x-intercept is when y equals 0. So you're going to plug in 0 for y. You're going to need to add or subtract with the k value. So you're going to need common denominators between these. So typically multiply your k value by x plus 4 over x plus 4. And then go through and simplify. I'm not going to show you all the math on this specific one, but if you do it, excuse me, you're going to get negative 3.6667. This keeps continuing on. If you need to see exactly how this works, please feel free to come by my room. Ms. Hinchman or Ms. Jennings can answer this question as well. You're essentially just going to subtract in this case because it's -3 and plug in 0 for y and then solve for x. Your y-intercept is a little bit easier. X equals 0, so you're going to plug in 0 for x and then simplify. So in this case, 1 over 0 plus 4 be 1/4 minus 3, and we're going to end up getting -11/4 once you get like denominators again and combine like terms. Your domain comes from your denominator, so which is where your vertical asymptote comes from. So -infinity to your vertical asymptote value union your vertical asymptote to positive infinity if you only have one vertical asymptote. If you don't, you would still have several union pieces together in between your vertical asymptotes. We've seen that before, but in this case, this is what our domain is. Your range is still going to follow the same guideline as before. I'm going to have everything from -infinity up to my horizontal asymptote at -3. I'm going to skip over -3 and move up to the top, which is what that says there. So -infinity to -3, union -3 to positive infinity. Is it increasing or decreasing? Your A value is going to tell you in this case in your general form. This is positive, so I will not have an increase. I will only have a decrease. And in this case, it will be the same as your domain. Again, same kind of commentary here about if you have polynomial functions, your intervals are going to change, but this is strictly for rational functions. So this is the guideline that we're typically going to follow in this case. The same idea about your end behavior is the number on the outside, your horizontal asymptote that we talked about. So in this case, your horizontal asymptote was -3. So I'm going to approach it from below and then approach it from above. And we get that number just right here from the same place we got our horizontal asymptote. This one, with the exception of the x and y intercepts, is probably one of the easier ones other than the graphs. It really just kind of depends on which key feature we're talking about. If you have any questions on this one, please don't hesitate to ask. You might want to take time now to kind of jot some things down, take some notes, and ask questions for clarification if you need any. Our last question that we're going to go over is question number 12. This is the last piece with our rational functions where we have higher order polynomials in our numerator and denominator. This is the type of form where we're going to want to factor everything as much as possible first, which I have already done for us here, which makes things a little bit nicer. You still need your restrictions. So let's jump on in. Wholes, where can I find these? These are going to be plug in your cancel factors from the denominator into simplified function to find the associated y. So what that really looks like in this case is I'm going to cancel the plus 2 and the plus 2. So at x equals -2, which notice that would be our restriction, that's what I'm going to plug in to that value. So -1 over, in parentheses, -2. I would plug that in to the simplified version right here. So -1 over -2 would be a positive 1/2 because the negatives would cancel right here if I plug this in on top. -1 over -2, plugging in for that x. And I get a positive 1/2. So just like we were talking about with our pothole situation, where the pothole is there in the road, it's there, but it's not there. Like the road's not there, if you get what I'm saying. So at that value, at -2, the piece that canceled, I'm plugging that in to find where the road should be, but it's not because there's a pothole. So we said it was 1/2. Decimal version is equally as fine. So that's how we find our whole on the function. Your vertical asymptote is the piece of your denominator that didn't cancel. So in this case, x equals 0. That's a little bit easier and nicer. Your horizontal asymptote is these little rules that we talked about. Top heavy, bottom heavy, and equal. So what that is referring to is this right here. We're going to look at the comparison of our leading terms. So if we're going to look at this, the x in our numerator has a power of 1, and the power in our denominator is 2. So which is higher, 2 or 1? 2 is bigger, so we would call this bottom heavy. So in this case, bottom heavy is always y equals 0. Top heavy would be if I had like 3 over x to the third over x squared, and you would have no horizontal asymptote in this case. It creates what we call a slant asymptote, but we are not going to get into that. If you want to know what a slant asymptote looks like, you can look at number 6 on the graphs. That kind of funky looking shape is what we would call the slant asymptote, but you'll not be responsible for that on this unit formal. Just a FYI. If, for instance, your powers are equal, if I had an x squared over an x squared, I want to look at the ratio of the leading coefficients. So if both of these were x squared, I would have a -1 over 1. -1 over 1 is -1, so y would equal -1 in that example. But in this case, we are considered bottom heavy, so y equals 0. Your x-intercepts set the numerator equal to 0 and solve. So what eventually ends up happening is you set y equal to 0 and you put it over 1, and then you cross multiply. So your denominator kind of cancels itself out because it gets multiplied by 0. So that's why we only need to pay attention to the numerator. So if we set that equal to 0 and solve, we're going to get negative 2, 0. However, we have a restriction that x can't be negative 2, so we have no x-intercept. Y-intercept, plug in 0 for y, again, does not exist. Domain, we're going to look at our vertical asymptotes. Comes from our denominator. So negative infinity up to 0, 0 to positive infinity. Your range, still going to be your horizontal asymptote. And again, remember this is if it only has one of each. We have 0 for both, so those are nice. Which obviously these now make sense because our asymptotes were at the axes. So we wouldn't have intercepts if we have asymptotes there. Increase or decrease. So I don't have like an a value in this type of equation, function. But what I can do is look again at the ratio of the leading coefficients, and I have negative 1 over positive 1, which gives me a negative leading coefficient. So in this case, it would be negative, so I'm not going to have a decreasing. It will be increasing. And again, it typically follows our domain. Now, our end behavior, we still want to look back at our horizontal asymptote. So it approaches a number either from below or above, depending if it's positive or negative. And it'll switch the above or below, but it approaching the same number doesn't change. I really appreciate you taking the time to try to better understand all these different pieces of the key features of graphing rational functions. I know it's a lot. Individually, it can kind of be not too bad, but as a whole, it can be kind of overwhelming. So I wanted to provide this as a resource for you guys and for others so that you can start to really master this and be prepared for not only your unit formal, but your final, and just in general, be knowledgeable about the topic. So if you have any further questions, if you need any more help or guidance on any of these questions, please don't hesitate to ask myself, Miss Mann, Miss Hinchman, or Miss Jennings. We would love to help you guys.